In this video, we're talking about normally distributed data and how to describe that data. So if you remember from last day, we were talking about the ages of graduate students and undergraduate students. And we discussed the fact that the age of the students is normally distributed. So if we plotted it, it would look like a bell-shaped curve. Now, if you look that up in a textbook, it might be listed under Gaussian distribution. We also talked about skewness and kurtosis. And if you'll remember, skewness represents whether or not the bell-shaped look even on the left and on the right side. And the kurtosis is how tall the bell-shaped curve is. Today, what we'd like to do is use some mathematical measures on the data to further understand these dispersions. So today we'll look at some graphs, and we'll talk about the distribution of the data using minimums and maximums and quartiles. Then we'll look at the mean or average of the data and the median of the dataset, and other measures of how to understand that distribution, such as variance and standard deviation and standard error, and how to calculate each mathematically. For this example, we've taken a random sample of graduate students and asked them their ages. We got 22, 24, 24, and 30. So our sample size n is 4 because there are 4 observations. The mode represents the most frequently observed value, so that would be 24. Because it comes up 2 times in our sample. The median is the middle number when sorted in ascending order, so that here would be 24 as well, because it lies directly in the middle of our data. The mean age of the students is the same as the average age of the students, so we'll do it by hand as a refresher. Add up 22 plus 24 plus 24 plus 30, that's the sum of our students, divided by n observations, so that's 4, is 100 over 4. So the mean or average age of the students is 25. Now we're interested in looking at measures of dispersion. So how widely dispersed is the data that we've collected? The range then is the distance between the smallest number and the largest number. So here that would be 30, subtract the smallest number, 22, that's 8 years. Quartiles are a little bit difficult to see here because of the small sample size, but they represent the values at the 25th percentile and the 75th percentile of the data. And they would be easier to see in a larger data set. The interquartile range, thus by extension, is the distance found between the 25th and the 75th percentile. So now let's look at a measure of dispersion. Say we draw a normal curve, so we can plot the median right here, and then we can show where the mean is. The median is the very middle number found in the data set, and in data that's normally distributed, so that means there's an even distribution on the left-hand side and on the right-hand side, you'll find that the median and the mean tend to be very, very close together. The variance then and the standard deviation will be describing the distribution on either side of the mean. The variance in some textbooks is represented by s squared. It's the average distance from the mean. The standard deviation is the root of variance, or s squared raised to the 1/2. The standard error then is the standard deviation divided by n observations in the dataset. Remember the term sums of squares because it becomes very important as we move through the course with analysis of variance, or ANOVA, and a linear regression. And it's important to understand that sums of squares and variance are related to each other. So if we're wanting to quantify how dispersed the data is, we can measure that using variance, and it represents the average value, subtract each value squared, all summed for each observations, and then divided by n. The mean of the observations is represented by x bar, and we calculated it before it was 25, being the average age of the students. So that would be 3 plus 1 minus 5, all squared, divided by the sample size n, so 36 over 4, the variance is 9. Standard deviation is the square root of variance, so the standard deviation is indicative of sampled observations. It helps us determine the 95% range of the data that we've collected. Our standard deviation is therefore the square root of 9, or 3. If age is normally distributed, and the mean value is 25, as we calculated before, we can add 2 standard deviations to the mean value, so that would be 2 times 3 added to 25, and the mean subtract 2 times 3. So that range from 19 to 31 will cover 95% of our data. So we would expect to find 2.5% of our population over age 31 and 2.5% under age 19. Standard error is interpreted somewhat similarly. However, it refers to the population that we are studying here, so that would be all grad students. Standard error is calculated as standard deviation divided by the square root of n observations. So if we take our standard deviation, 3, over the square root of 4, that's going to be 3 over 2, so our standard error is 1.5. Then we take our standard error and multiply it by 2, the mean, and the same on the other side. And for normally distributed data, we expect 95% of the population will have an age between 22 and 28. And again, 2.5% will be older and 2.5% will be younger.